Okay, well, I think we're about to start. Please confirm that the sound is in fact okay. Can you hear me? All right, I think you can hear me. So let's start. Today's webinar is called Video Analytics Based on Neural Networks, Their Key Advantages and System Settings. And essentially it means the explanation of why we've gone the deep learning path and what you can gain from it. So let's begin. I think I should start with introducing myself, and my name is Alex, and I am the development team leader here at Eocortex, and my team is responsible for developing new video analytic modules and improving the old ones, should we have the time to do that. Somebody says we have a terrible echo. Somebody please confirm that. Well, somebody says that sound is okay. Somebody says the echo is there. Well, all right. Well, I think, okay, maybe a little jolt. Okay, let's keep going. So, my team here at Eocortex is responsible for developing new analytic modules and improving the old ones if we have such a chance. And developing solutions based on machine learning and computer vision can be a challenge in and of itself, because what you have to do is essentially train a very dumb machine to do something that humans have been doing for years on end. Like facial recognition, for instance, or counting people. You name it. There are lots of tasks that we can do with video analytics, and each of them is pretty difficult. However, in recent years, we as a company and as researchers have gained a new way of creating analytics that are way smarter than before and work much better than before. So let me tell you all about those. And just a reminder, during the webinar, you'll be able to ask questions. However, I won't be answering most of them until the end, because I want to keep going. So if you have a question that is particularly relevant to what I'm saying at the moment, then I will probably answer it. But most questions will have to wait until the end. So please write them down if you have questions, and I will be more than happy to answer them, but a bit later. So let's keep going. Well, some of you might know what a neural network is, what it does, and why it's good. Some of you might not. And today's webinar is aimed at bridging that gap. So I would like to tell you all about those, how we use them, and what are the key benefits. So let's start with the most basic definition of a neural network. A neural network is essentially a mathematical model that is intended to solve tasks by looking up patterns in the actual training data. So the difference between neural networks and conventional machine learning methods is that apart from conventional methods, neural networks basically fit themselves to the data that you provide. Meaning that if you give it a bunch of data and give it some rules as to how it should train itself, it will probably be able to learn to do the task pretty well. Like facial recognition, for instance, once again. A neural network can learn to recognize faces out of hundreds of thousands or even millions of people if trained right. Just like humans probably, or maybe even better sometimes. So the use cases of neural networks are include, but are not limited to, image classification, machine translation, and speech recognition. Here at Eocortex, we're mostly interested in the first category, which has to do with images. So we detect objects, we recognize objects, we classify objects, we do lots of stuff, but everything that we do has something to do with image processing. Okay, let's jump right into that. So why have we started using neural networks? Well, the reason is actually pretty simple. The first and foremost, neural networks technology has become more affordable than ever. It's not like neural networks haven't been around for dozens of years. In fact, the first developments in the sphere have been going on since the 50s, but it's only been possible for about 10 years to be running them on decent hardware. So the main thing that's changed since the 50s is that the science has gone much further into understanding how human brain and human eye works, and coming up with ways to describe that behavior and train a machine to do that. And also, computing power has risen substantially. And today, you can buy a relatively average PC and still be able to run neural networks on it, which is exactly what we use. Of course, if you have CPU or GPU power, rather, you will be able to run your networks much better, but in essence, you don't really need that, although we do recommend it. Well, the second reason why we started using neural networks is that neural networks are well suited for video stream analysis, which is exactly what we do. If you know something that's called convolutional neural networks, then you might know everything about how we do stuff here, but essentially we use certain types of networks that are designed to work specifically with images, making our tasks much better than before, and making us, allowing us to create much better solutions than before. And the probably most important reason why we have gone the deep learning way is that neural network technology allows us to achieve much greater precision in a wider range of conditions. So not only do modules work better, they are also more robust, meaning they will be able to work in a wider set of conditions, meaning more models of cameras that work fine with modules, meaning larger illumination range and all that. So neural networks, apart from conventional methods, fit themselves better to the data in terms of being able to solve tasks more efficiently than before. So whenever we do something with a conventional method, we basically tell the machine what to do. And we don't really, we might not even know exactly what it is that we know about certain behaviors. For instance, if we have a task of recognizing a person's age, you might know that some traits of a face might represent greater age. For instance, if you have if you have gray hair, for instance, that means that the person is probably older. But this is one of the more obvious features that you can pick up. But in fact, what your brain does is it learns from thousands of faces you see every day, and then you're able to recognize a person's age more or less accurately without actually looking for specific patterns, because your brain already knows. It's done it thousands of times before. And with conventional methods of computer vision, you don't really have that opportunity, because you have to specifically program exact features that it should be looking for. And that isn't the case with neural networks, because they, in turn, work almost exactly like your brain. They actually look for patterns themselves, and they fit themselves to the data. So they might end up having extracting features that you, as a person, might not even know about. You do use those features, but you never actually consciously think of them. So sometimes neural networks can become really difficult to decode, but the power of them and the magic of them lies exactly in that feature. They're able to extract features themselves. They don't need you to program them. You basically give them data, you give them certain rules to train themselves, and they do it. And it works like magic most of the time. And also, one of the reasons why you might want to use neural network over the conventional methods is that neural networks make great use of GPU power. So not only do they work faster, but they will you will be able to lower the load on the central processor by using a video card. Well, the GPU is a graphics processing unit, which is the core of the graphics card. So if you use those, your CPU will be free to do other tasks, is essentially what this is. All right, let's keep going. So currently, in Eocortex, we have 4 modules that operate using neural networks, all of which are recent ones. So the first one is hard head detection, a module that basically allows you to detect whenever somebody's wearing a hard hat or not wearing it, and signal an alarm whenever it detects the person that's not wearing a hard hat. That's the essence of it. And then we have a people counting in queue solution that actually has existed before, but recently, as of version 2.5, we have updated it to use more advanced technologies that allows us to count people more accurately and in a better environment, so you don't have to use specific cameras or anything like that. But we'll get to that. The next big one is the face recognition, the module that probably most people are interested in. So it just like people counting in queue, face recognition has existed before, and it has been in our software for years now. But recently, in version 2.8, we have greatly updated it to use basically all neural networks pipeline that allows us to greatly use the GPU resources, free up a lot of CPU, and also run our recognition much more accurately than before. And I'm about to show you that. And next one is the new module. Also, it's called a unique visitor counting. This one uses most of the technologies from the face recognition modules, with a few extra tricks to make it work like it does. And what you have to know about it is that it probably inherits about 90% of what a regular face recognition does, but it's also able to count people that are not even in the database. So you have a lot of people coming in and out from the facility. The module will see them all, and whenever you want to see a report, it will automatically analyze them and provide you with a pretty detailed data on when a certain number of unique visitors have visited the facility. All right, so on to the benefits of using neural networks. Here in the slide you can see a screenshot of Windows Task Manager running the Eocortex standalone with a face recognition basic module, the old one basically. What you can see in here is that we're running about 70% of our CPU just from using the server. And I have to tell you that we're running 4 channels at 2 megapixels, and we're running 4 modules of face recognition basic. And if you ask me, that's quite a lot actually. I would like to be able to fit more face recognition modules on my server, wouldn't you? So in version 2.8, we have allowed that. So here you can see the face recognition complete module, rather the screenshots of it, the screenshots of it running on the system. And here you can see that apart from having 70% load on the CPU, we now only have about 22, a decrease of 3 times actually. The situation is exactly the same. We're running 4 cameras at 2 megapixels. Each of those cameras is running a face recognition module, and we have a pretty dense people flow, meaning that each second, or rather each moment in time, at least 1 or 2 people are passing through the camera. So at any point you have people in the frame, and the module is working all the time. So it's running at its not maximum capacity, but it's running a pretty heavy load actually. So here you can see it's about 70%. Now we go down to 20. And how do we do that? Well, we do this by using a GPU actually. So on the slide to the right, you can see that we have a task manager open to the GPU tab. And if you look closely at the graph that says CUDA on top of it, we're running at about 30% of something. And that something is actually the GPU core load, which means that all the work that before had been done on the CPU is now completely offloaded to the GPU. The CPU is free. The GPU is doing all the heavy lifting. And the module is running much faster than before actually. And if you look closely as well, you'll be able to see that we have a lot of room to spare on the GPU. Because apart from the CPU, which you cannot really load up to 100% at any point, because it might go bad if you do that. Also, the system will be kind of sluggish, Something might not work when your CPU is pegged at 100%, which isn't the case with the GPU, because you can run it at 100% all the time and it won't really make a difference that much. So by offloading all the heavy lifting to the GPU, we've actually given more resources to the system as a whole. Okay, I have a question that I want to answer. Why not using both GPUs? Well, the reason is pretty simple, actually. Those GPUs are not equivalent to each other. The GPU 0 is an integrated GPU, an Intel graphics something. It's not very powerful. It's not really designed to be running neural networks efficiently. It's a small GPU, and it's not really a powerful solution. You can't really do much with it, and we just use it for video output in this case. But the second GPU, as you can see, is an NVIDIA GeForce GTX 1060, which is a decent GPU, and it's designed exactly to run heavy work like graphics, gaming, all that, but also running neural networks, because as it turns out, GPU architecture is perfect for neural networks. So that's the answer to the question. Those GPUs are not equivalent, but if you had two of the similar GPUs, the GeForce 1060s, you will in fact be able to run neural networks on both of them. So that's the answer. Now let's move on to the people counting in queue module. And here on the left you can see the old module that you probably have seen before. It used to be in the software before version 2.5, and what it did basically is you had a camera pointing downwards, so straight down, and you would have to count people based on how they move, basically, because, well, you can't really see much from there, from that angle, but it was an absolute requirement to have the camera set up like this, because the module wouldn't be able to work any other way. And to tell you a secret, well, not really a secret, but that module, the old one, didn't really count people, but rather it counted the estimate of motion produced by however many people we thought were there. So one person produces an X amount of motion, two people produce 2X amount of motion. Well, at least on paper. That's not really the case in most of the time, but it worked somewhat accurately. You could rely on it, but it wasn't really enough. So we went out of our way to create a new solution that employs neural networks that do actually count people. So here on the right, you can see another screenshot that shows a completely different camera setup, whereby you don't have a camera that's pointing straight down, but rather it's a usual, more or less regular overview camera that you can use to monitor not one counter, but two or probably even more counters. Here you can see the letters 7, 8, 9, 10, so 4 counters. And theoretically, you could use one camera and set it up so that you can monitor 4 counters at the same time and use one module for that. So when the camera is set up like this, you have people showing their faces, showing their heads, their shoulders, and this is exactly what the module uses. The new people counting in queue module analyzes the heads and shoulders in the zone. So here you can see an outline of a zone called zone 1, and below that you can see the number of people that are currently in the queue, which is 4 apparently in this case. And if I were to enable debugging data, you would be able to see, in fact, that the module is counting heads and shoulders of those people and outputting the correct information in the interface, apart from the old solution where we had rough estimates of what those people were doing. So the benefits of using a neural networks-based solution is that now, when we are actually counting heads and shoulders, we don't have to worry about any shopping carts, any kind of extraneous objects, like, you know, maybe there's something in the way of the camera and it's moving, like for instance, maybe, you know, a bag or anything. So whenever a person is holding a bag, or maybe 2 bags, it produces more motion than before, and our estimates go way out of whack, which isn't the case with the new module, which doesn't really care about any bags or shopping carts or anything like that. Whenever you have 5 people that are holding any amount of bags or shopping carts, it will still show up as 5. Well, at least most of the time, whenever they're not covered by each other, which is a pretty good point because there are certain aspects of the module that need to be taken into account, because in this setup, you may be able to see the situation where one person is covering another. In this case, the module will, of course, not be able to see everyone. So the trick is to set up the camera so that the module, or well, the camera, is able to see all of the people without having to sacrifice much of the overview. All right, I'm seeing a few questions that I want to answer. Well, one question rather. What about using 360 degrees cameras? Do we need 4 modules for face recognition? Well, if you're talking about the fisheye cameras, counting people, okay. Well, one thing that you have to take into account is that this module relies on knowing the actual geometry of the people. So if it's been trained to see heads and shoulders in the way that it has, meaning having no distortion or anything, then you will have to provide it with the same kind of image. So if you're showing a very distorted kind of image where a person's head might be tilted to the right and his shoulders might be, you know, all over the place, well, then it's probably not going to work very well because, well, from the module's perspective, this isn't really a person anymore. It treats it as a false alarm and will not display them as people actually. And a multi-sensor camera. Well, I don't really understand the question. What is the multi-sensor camera? Okay, well, let's carry on. I will answer that question a little bit later. So, you might wonder, if those new modules are so advanced and they're running some sort of different technology, they require GPUs and all that, well, what are the particularities of setting up such a system? Well, the first and the most obvious one is actually using GPUs to accelerate your neural networks and free up the processor, something that I've mentioned probably 5 times already. So what you have to do is either buy a pre-fitted server with GPUs, or just buy one off the shelf and put it in there. The benefit of using such a server is that you don't have to pay a lot for a really powerful CPU. You can fit it with a pretty regular CPU, and since the load is offloaded to the GPU, it won't have to work as hard. So you might save a buck or two on there. Second one is the neural networks are fascinating. They work in a wide variety of conditions, so they might work even in poor camera or video stream settings. But the better circumstances they're in, the better they work. So if you set up the camera in a way that is dictated by the specification, so if you make the conditions better, what you'll likely see is that the module starts performing better as well. That wasn't always the case with conventional methods because they were pretty much fit to do exactly one thing. And they were fitted to specific conditions. They didn't really work well everywhere. So if you have a camera change, the old modules would probably just break or not really work any adequately. Whereas with neural networks, you still have a chance to run them somewhat nice. So they will probably be able to count people even in really poor conditions. But why make life any harder? If you can, you should definitely try to make the conditions as well as possible, or as good rather as possible. And I'm about to show you how. But let's get to the next point. Well, the only actual change in the setup process, apart from having to install a video card, is installing a separate set of files via a neural networks installer. What this does is it basically copies the files for neural networks onto your computer, and then you're done. The operation is now complete. After you've installed neural networks on your computer, you're able to start using your new modules. It's about as simple as that. So there is no actual variation in the process for the end user. The only thing that's changed is actually the initial setup and the hardware. So those two things are different, but all the rest of the process is exactly the same. We've actually done quite a bit of work to make that happen. Okay, let's move on. And now I'm about to show you, or rather explain to you, the difference between different conditions that the modules might be operating in to kind of illustrate how the conditions may be important for ensuring that the module works best. Well, if you can see the picture on the top left, well, it's exactly the same image underneath, but we've applied a series of transformations to each one of them. So the first one is, if you can see, is kind of blurry a little bit. And as you can imagine, extracting features from such an image can become a little bit more difficult. Well, who am I kidding? It's much more difficult. So I would recommend setting up the camera so that there is no kind of blur, there is no motion blur or anything like that. The image has to be sharp. It has to contain details, because that's exactly what neural networks do. They extract certain details and they process them. Whenever the image is blurry, there's fewer details and the work becomes harder. Once again, the modules would probably work on a blurry image, but you shouldn't really count on it. The second image, the one on the top right, well, this image doesn't really appear any different, but if you look closer, you'd be able to see that the resolution of the image is actually pretty low. I would say it's about 4 times lower than the one at the bottom right. So the problem with low resolution, well, you still have details, obviously, because you have like bigger pixels and stuff. But at the same time, the details become less pronounced, actually. Well, it's not the same as blurring the image, of course, but if you're lowering down the resolution, the number of details becomes smaller as well. So when the image is really low resolution, then even the human eye would probably have trouble understanding the details, and neural networks is no different. Okay, moving on to the image on the, well, at the bottom left. Well, do I really have to comment anything here? Well, the image is full of artifacts, and it basically doesn't even look real. And that's the whole thing with the neural networks. They learn, and they are specifically trained to be able to recognize real-life scenarios, real-life images, real-life people, real-life faces, all that. But this doesn't exactly look real-life. So we might train a network that would specifically be able to decode people from an image like this, like the one in the bottom left. But that's not exactly what we do. Instead, what we want is to achieve the maximum accuracy on normal conditions, and this one definitely does not qualify. Apart from the one at the bottom right, because this one is an example of a clear image, the illumination is perfect, the level of details is perfect, the resolution is perfect, and that's exactly what we should be aiming at whenever we're setting up a system. So everything is pronounced, you can see all the details, you can probably even read the writings on the car back there. You can see all the skies, you can see all the clouds, so everything is looking great. It looks realistic. That's exactly what the neural network wants. Let me give you a more extreme example of that. So here on the left you can see an image that looks somewhat realistic. It's an image from an exhibition somewhere. And the level of detail seems to be, well, somewhat decent. But if you look closer, well, on the right, you have a close-up screenshot of one of the people closer to the middle of the image. And ask yourself, how difficult would that be to identify this person? Well, I'm sensing that it's not that easy. Well, it wouldn't be easy for me, at least. And once again, neural networks are exactly the same. If you cannot recognize this person with your eyes, then the neural network will probably not be able to do that either. Okay, here's a good question. What resolution do you need for people counting in queue? This one is a bit complicated, actually. But In short, what we recommend is about 2 megapixels worth of camera, and then because the counting is executed in actual zones, if I go back a little bit, you can see here we have, on the right, we have a certain zone that is outlined in orange. That's where the neural network is working. So the size of that particular area must be greater than 500 pixels at its larger dimension. So that's exactly what the answer is. Your zones should be at least about 500 pixels in its larger dimension. That might sound a bit complicated, but it's not really that difficult. So you take a 2 megapixel camera, you take a zone that's about, I don't know, 1/5 of the image, and it should be working fine, provided that the people are not really far away where you cannot really see the features once again. So the example that I've given you before, this one, really illustrates what happens when you have people that are way far away from the camera. So even though the quality looks okay in general, you cannot expect to be detecting faces anywhere farther than the middle of this image. The people that are in the front will probably be okay, even though they look kind of blurry as well. But the ones further away, there's no chance of detecting them whatsoever. Let me put it that way. Okay, let's move on to the illumination requirements. Once again, neural networks want to have the image as close to reality as possible, and they want the level of details to be exactly the way human eyes can see them. So if we look at the first image, here we can see that you're barely able to see anything, really. If I saw that image for the first time, I don't think I'd be able to tell what's on that. Can you? I certainly can't. So the second image is kind of on the opposite end of the spectrum, where you can actually see the details, but the image is greatly overexposed. So everything is really bright. Darker colors are not pronounced at all. So the actual image is also a bit offset from what a neural network would expect. In this case, it might work again, but not very well, I suppose. The third image looks better, at least to me, but the problem here is that the contrast level is not very high. I would say it's really not high enough, because everything is not, well, you can see the details, at least somewhat, but the overall quality of the image, well, that's not a photo you would like to take, right? It doesn't really look something you would want to remember like this. Apart from the last image, where everything is exposed properly, you can see all the faces, you can see all the details, you can see all the expressions, all the shadows are well pronounced, all the illuminated areas are well illuminated. Everything looks normal to an eye, and also to the neural network. Let me tell you now about the other modules that we have that run on the neural networks, and we'll get a little bit into the specifics of how they work and what they require and what the parameters of them are. So the hard head detection module runs on neural networks, just like the Q counting and the face recognition, which allows it to be able to detect hard hats of different kind of shapes and colors. But well, most hard hats look similar, but they're not exactly the same, and they can be, the colors can vary greatly. So here you can see 6 ones that are, well, they look somewhat similar, but they're completely different colors. However, the module doesn't really care about that, because as long as you have a hard hat that looks like a hard hat, it will most certainly work. And the response time for any of those hard hats is about 1 to 3 seconds, depending on the conditions. And the false alarm rate is about 1 to 3% as well, meaning that out of 100 people that are wearing hard hats, the module might declare 1 to 3 of them as not wearing hard hats. So that's what that means. Okay. Oh, I see a very nice question. WDR Pro functionality activation on camera balances out exposures to get perfect picture quality. I have to tell you something. We've actually faced that kind of cameras while working on face recognition, and what we have discovered is even though the image looks cleaner, and obviously, yeah, the exposition becomes better when you turn that feature on, there's a downside to that. Because it requires more processing power to run that feature. Some cameras just cannot handle it straight up. You might see some artifacts. The image might get blurrier. You will definitely get motion blur, is what we have discovered. So face recognition obviously requires face to be to look normal. Well, let me put it that way. So the features of the face should be clearly visible. But whenever you turn WDR on, you might see that the person who's moving at a normal speed, like 4 kilometers an hour, might become really blurred. So the face will be really blurry. You will not be able to see any features whatsoever. I wish I had a picture to show you. So to answer your question, well, not really an answer, but to make a comment, WDR is great, but you have to be careful about it because if you turn that on, you should really check whether or not the image still looks okay from the perspective of details. So that's something you should definitely check out when using that. Let me get back to the presentation now. So the minimum height of people to be analyzed is about 120 pixels. Well, if you factor in the 2 megapixel camera, well, you get the idea of how large the person should be. Then the frame rate, well, the minimum frame rate is about 9 FPS, but I would recommend going a bit higher if you can. If you have a 30 FPS camera, for instance, then those 20 extra FPS will not be wasted because the module analyzes all available frames. It's just that it picks the 9, well, out of those 30, there might be more good ones than there are out of 9, right? So if you can, you should provide more than 9 FPS to the module, but 9 is also okay. The tilt of people in frame is about 15 degrees, and what that means is, well, when you install a camera, usually they're installed up near the ceiling or anywhere that's high up, and the trick is to point the camera so that the people are not viewed from above, like not completely straight down. You really should point the camera to look further into the scene to be able to see people from the side, not from the up. You don't really want to see people's heads from up high. You want to see the person as a whole because the module only works on those people that are fully visible in the frame. Then camera direction angle is less than 45 degrees. That ties together with the previous point in that whenever a person is, your camera should be both angled properly horizontally, and it should be looking not straight down, but further away. So you should really make sure that the people that are in the frame can be clearly visible in full from head to toe, and that they should not be tilted anywhere. So that's the main thing about this module. And the kind of image that you want to be using is a color image. So night mode on cameras doesn't really work. We have tested it, in fact, and it kind of works, but we wouldn't recommend doing it. In fact, I don't think you should be doing it because the quality decreases greatly. So we explicitly specify the color image as our choice for analyzing video with hard head detection because it's simply the better choice. Let's move on to the parameters of the people counting in queue. And let's compare it once again to the old module. The only kind of position that you could possibly use with an all module is a camera that's positioned completely downward, so looking straight down vertically. And this isn't exactly the kind of camera that you want to be using, really, because, well, it cannot see really anything. So we have to install a separate camera just to run the module, the people counting in queue module. And that's not something that people want to do. Spend an extra camera, an extra amount of wiring to do one specific task isn't exactly what we're looking for. So instead, with a new module, what you're using is a regular overview camera that can be tilted at about 45 degrees to the horizon, or well, to the Earth plane. So this approach is more flexible, and it allows to use actually fewer cameras, and still achieve the same task. And the operating procedure, as it's called here, is the one that I mentioned before, whereby in the old module we basically didn't look for people, but rather for motion. And the amount of motion produced by certain people should be different according to our estimates. And that's exactly how the module operated. It basically divided the amount of motion by a certain constant that would represent the amount of motion deducted by one person. So there's that. In the new one, instead, we have a proper head and shoulders detection system that takes care of all of this. So we don't have to worry about any estimates. It works exactly like it sees the image. And the recognition accuracy is about 75 versus 89% between the modules. But I would say that 75 for an old module is a pretty generous estimate. And the new module can work even higher than that. So 89% is an average. So if you set up the cameras well enough, you should be able to get it to higher numbers. Well, let's get to the technical stuff once again. The tilt angle is 40 to 70 degrees. Just like I mentioned before, 45 is about the average one, but anything from 40 to 70 will probably do okay. The visibility of the person. Well, this is a pretty important parameter where it says that at least 70% of the area of the head should be visible for the person to be detected. And that's something that I mentioned before, where you have to actually be able to see the person in order to be able to detect them. So it's a responsibility to put the camera so that the hue is visible and there are no overlappings or anything like that. Speaking of overlapping, the maximum overlapping allowed is about 30%. But if you can, you should really get it to down lower than that. That's the maximum amount you can afford. The camera resolution, once again, as I mentioned before, is about 1 to 2 megapixels. 1 megapixel is suitable for smaller rooms where the hue is actually closer to the camera. So you don't really need that extra pixels. The 2 megapixels are more suitable for larger rooms, and you can go from there. So anything that's higher, like for instance maybe 4 megapixels, will do better for cues that are further away. However, you really shouldn't be analyzing cues that are at the opposite end of a 100 square feet room. That's not something you should be able to do. And well, 1 to 2 megapixels is pretty much the standard here. If you need to know more about it, please go ahead and ask the questions. Now, the image is once again color image because the network was trained on color images and it expects to see color images. Once again, we have tried it on black and white, and really that's not something you should be doing. Okay, well, let's get to the best features of the new face recognition modules. So as you have seen before, face recognition basic eats up quite a lot of the CPU, well, about 3 times more CPU than the new face recognition complete. But not only does it eat about 3 times more, it also lacks some of the features that the new module has. Like for instance, the basic module has a fairly severe limitation of the amount of faces that can be analyzed at one time. Like for instance, you have a really dense crowd of people walking through an entrance. You might have like 5 to 10 people at the same time going under the camera, but the basic module will not be able to do that. It will not be able to recognize all the faces. It will not even be able to capture them all at one time. However, the new complete module will definitely be able to do that, as we have tried numerous times before. The next feature that we particularly like about the face recognition complete that was lacking in the previous module is the determination of gender and age, which is a pretty standard request from what I can tell in the industry now, and it works fairly okay. Judging a person's gender and age from a face alone seems to be a kind of a tricky task, but the neural networks are definitely able to handle that. So the next one, the next point that we are particularly proud of is recognition of people wearing glasses, headgear, and beards. So basically, whenever your appearance is changed slightly from the sample that is in the database, the complete module will still be able to recognize those people. Well, provided, of course, they're not wearing a full face mask, but that's not really something that we do. So if a person is wearing, large sunglasses that are covering like half of his face, the face recognition complete module will still be able to recognize them. You may try it on your own and see how that works. It works like magic, in my opinion. And the next feature is search in the archive. So when you don't really have a database, or rather you don't have a person in a database, but you want to see when the person was under certain cameras that have face recognition, well, with the new module you can do that. So if you have someone that you want to find, you take a photo of them, or take existing one from the archive. You run a search in the archive, and you will have all the times that the person has appeared on your premise for the past, as long as the archive is available, actually. And the recognition accuracy that we claim is, for the old module, it was about 92%, roughly. I would say this is a pretty mean average, and the new module is claiming a bold 99.9%. Well, of course, that depends on the conditions, but when you're able to set up the conditions to be somewhat nice, then the module will work pretty good. A question is, do you need a dual lens IP cam for face recognition? A dual lens cam? Well, no, you don't really need that, because we've been using regular cameras for the past, a year, I think, since we started developing the module, and they work fine. You don't really need a dual lens setup. It works with a regular camera just fine. Well, if you're asking, if your question is more specific than that, then please ask it in the question section. I will get to it later. Let's keep going. So the light parameters, well, not the light, but the more like a camera setup parameters. Well, the most important thing for facial recognition is actually the video stream quality, the one that we've talked about before. So the light source should be balanced, meaning that the face should not be overexposed, it should not be underexposed, it should be just right. Everything else in the image can be underexposed or overexposed all you want, but the faces themselves should be pronounced, and they should be recognizable by people. And the better the faces look, and the more realistic they look, the better the module will work. Camera resolution, once again, is 1 to 2 megapixels, pretty standard. No fancy cameras required. Definitely no dual lens. Like Pascal suggested, you don't really need that. The next one is the distance between pupils of the faces to be recognized. It should be about 30 pixels. This is a rough estimate, and it means that you shouldn't be expecting the module to be detecting faces that are like 4 pixels square. You need a decent quality image to be able to recognize them efficiently. And a good way to tell if a face is good to be recognized or not from a resolution standpoint is to have it, measure the distance between pupils, and we provide a metric of 30 pixels. That's your go-to metric. It's a little bit more complicated than that, but that's your starting point. Well, and the point that is also quite important is that the angle between phase direction and the lens axis should be no more than 30 degrees. Let me explain you that one. Whenever people appear in the image, they might be looking in different directions. Like somebody's, walking and looking straight in front of them. Some people are down in their phones, looking basically at the floor, and some people are looking up at the cameras for some reason. Some people are looking to the right, to the left, and so forth. What you want to do is install the camera so that most people are looking somewhat in the direction of the camera, and the angle that we provide that is good for the faces to be properly recognized is about 30 degrees. So what you should do is install the cameras so that the most people are facing the camera actually, and the angle of the camera should not be great. It should not be looking straight down the floor. It should be as parallel to the ground as possible. It doesn't matter if some people are further away. It's better for the module to see the entirety of the faces. And since most people are looking down at their phones nowadays, that's something you should consider. Okay, and the main takeaway I think that you should be picking up from today's webinar is that neural networks operate similarly to a human eye, and I would add to a human brain as well, because it trains on images that are good in a person's eye. So if we train a network, we provide a series of images, thousands of images usually, that look okay, where you can recognize faces properly, where you can kind of see all the details, where the lighting conditions are fine, and this way we achieve, we will be able to create networks that do the job properly, that don't really that look for right patterns, that are very accurate, that don't really give many false alarms and stuff like that. So we have to limit the range of available conditions somehow, even though in the case of neural networks that range is a bit wider. Still, you have to realize that if you cannot recognize a person from an image, a neural network will not be able to do that either. So if we're looking to use more advanced technologies, there are a few steps to be taken. Well, that kind of concludes the at present part, and now I'm going to talk a little bit about the future developments of Eocortex. So what we're going to do next using the neural networks technology. And there are three currently. The first is a smoke and fire detection module that we currently have already, but we're not really satisfied with its quality, so we're developing basically a new one from scratch that will be able to do its job much better. We're not finished with it yet, so I cannot really tell you whenever that's going to come out, but the progress is looking good. The next one is a suspect search. Well, this module has been around for a while now, and it's been developed, I don't know, maybe like 5 to 7 years ago, and technology has gone far from there. So what we're basically going to do is to update the suspect search, a module that I hear many people like and use, with a new technology that will allow it to be more precise, to achieve much higher accuracy, and then provided that you're using a GPU, the module will be able to offload more resources from the CPU. So you will see the difference. Now, the face recognition, well, there isn't exactly going to be a revolution anytime soon, probably, in the quality or resource consumption, but we're going to continuously work on the module to be able to improve its rough spots and improve the performance and improve the accuracy at least a little bit. So we're focused on providing the best face recognition experience that is possible. And once again, let me reiterate why those kind of modules are actually the future. So the first point is that they help to solve more complex and specific tasks compared, to the conventional methods, because there are some things that conventional methods outright cannot do. Like, once again, the age recognition. You cannot really program a certain algorithm to recognize a person's age from an image, because it would be too specific to a certain situation, and it wouldn't work in most of the cases that you might face. So it's basically not really viable to do something like this without the power of neural networks. So this is an example of having neural networks to be kind of irreplaceable. So before we had neural networks, we couldn't really do that properly, and now we can. The next one is higher accuracy of video analysis modules. I would add of existing analysis modules, because there are some things that conventional methods of computer vision can do fairly well, but they can't really do it in all the kind of conditions that you might imagine. And neural networks might help with that as well, because even though on average it wouldn't be working much more accurately compared to the old one, but it would probably work better in most cases. So that's an important one as well. And once again, the point that I've been talking continuously about today is that you can use a video card, or graphics card, a GPU, whatever you might call it, to actually offload some of the work that has been being done by the CPU, and have it freed up to do some other tasks, like maybe use more cameras and stuff. So this one is probably the most important of all. And that probably concludes my presentation for today. And now we're going to move on to the answering the questions part. So if you have any questions that you've been stacking up this whole time, now is a good time to ask them, and I will be answering them as fast as I can. So you can go ahead and ask them either in chat or the questions section. I will be reading both. And let's read the module that is, or the question that is the latest one. The question is about using fisheye cameras related to the mix of deep warping module and some other, like face recognition or counting in Q or shelf fullness. Whatever we may analyze from an image taken from the ceiling. Scanning for image. Okay, well, yeah, okay, I see what you're talking about. The question is basically, can we use fisheye cameras to run other modules off of it, like maybe chain them together. We dewarp the image and we then pass it to the face recognition module, for instance. And well, to tell you the truth, we don't really like doing it this way because whenever an image is dewarped, a certain level of detail is lost completely to the dewarping algorithm. And some details are actually made up by the dewarping algorithm. So whenever we're like trying to recognize a person from an image, well, with the amount of details added to the image during dewarping and the amount of details taken away from the image during dewarping, we don't really, well, the image isn't really clean anymore. It's a completely different image, and face recognition might not really, might not be very kin to working with this kind of image. We might reconsider that in the future, but for now, this is the way it is. So only some of the modules will be working with the dewarping module, excluding face recognition, counting in Q. Shelf fullness will probably be able to work with fisheye cameras, but not to a great degree, because once again, distortion is really great, and it doesn't really make a lot of sense to be using them to analyze a distorted image. And as of now, we don't really support chaining the modules anyway, so that's not exactly something that's coming very soon, I'm afraid. Any more questions? Oh, well, maybe crazy questions. Are there also maximum specifications? Well, I think you have to elaborate on that because I don't really understand.